Yeah.
Take it away.
Well, thanks, Doug. Yeah, so been forecasting for 8 seasons, ski patrolled a little before that, and got my master's at MSU. And worked on this study with Doug and Carl, looking at the effectiveness of extended column tests, propagation saw tests, and compression tests. And I assume probably everyone in here is familiar with those tests or uses them for work. How many people use these for their jobs fairly regularly? All right, cool. So I won't get into too many details of how we do those, but we have the extended column test on the right here. That's a 90 centimeter wide by 30 centimeter deep column, and we apply force to one side to test for how hard it is to initiate a fracture and whether that propagates or not. And the propagation saw test looks more just at propagation. It doesn't get us a gauge of force that to initiate a fracture, but gives us an idea of how likely a fracture is to propagate. And then I don't really have any pictures of compression tests for some reason, but that is a 30 centimeter by 30 centimeter column, and you apply similar force that you would in an ECT. And with the compression test, you also give a measure of shear quality on that fracture of whether it's really clean shear to a really rough shear, and that can kind of gauge propagation propensity. I was told I need some videos to keep things exciting. So this is a long propagation saw test that I was messing around with. I think it's 2 meters, so longer than the standard. But I slowed it down just for excitement.
Attention's on the edge of our seat.
You can kind of see the weak layer shooting out there, and I'll play it one more time. So you can watch the top of the slab. It kind of collapses first on the right and slowly transfers over to the left. So it's kind of a cool representation of the fracture mechanics that are actually occurring in an avalanche. And so these are small block tests that we're trying to get a gauge of whether the snowpack is stable or unstable. It's kind of the basic thing we're looking for. And so our objective is to look at false stable and false unstable rates for each of these tests. And we focus a lot of the time on false stable rates because they're the most consequential outcome. This would be if we get a stable result on a slope that's unstable, and if we go ahead and open that slope or ski it, it has high consequences of injury or death. And so we really want to minimize those. On the other hand, if we get a false unstable test, if we get an unstable result on a slope that's actually stable, and therefore we don't ski it or we keep it closed for the day, no one's going to get hurt, but we might lose the chance to ski that run, or we might lose profit from having the ski area open or having a highway closed or something. So those aren't ideal either. So we want both of these to be low. There's been quite a bit of previous research on each of these tests. It all has limitations, and our study certainly isn't free of limitations or bias, but they've used different methods of assessing the effectiveness and have a wide range of sample sizes that are in that left column there. And one of the biggest challenges in this research is determining whether a slope that the test is done on is actually stable or unstable. Because a lot of the time we don't really know that unless it actually avalanches. So some of these studies have dug a bunch of pits and done tests on slopes next to recently triggered avalanches or WUMPs and considered those as being on unstable slopes, and done a bunch of tests on slopes that were tested with explosives or skiers and considered those as that didn't slide and considered those as slopes that were stable. A few of them have used a method that we use that I'll go into more depth on, but determining whether the slope is stable or unstable based on the user's rating of that slope stability, just saying whether it's good stability to very poor stability, and that's kind of a subjective assessment based on the user's knowledge of the snowpack and weather history. So the ECT up at the top, we see false stable rates up to 19% that people have found. The PST was quite a bit higher at 30 to 44%. And the compression test covers that whole range, but if we take out this kind of outlier in the second to bottom row, it's up to 10 to 22% false stable rates. And this one is, in this study, they used a pretty low threshold for saying a CT is unstable. They said anything less than 14 hits was unstable, where these other ones used less than 21 hits. So I think that's a big reason that one is quite a bit higher. The false unstable rates, up to 22% for the ECT, 14% for the PST, and then getting quite a bit higher for the compression test, up in the 40s and up to 79% in one study. So even though the compression test has similar false stable rates, it's got quite a bit higher false unstable rates in these previous research. So it can keep us from getting into trouble, but it would also keep us from opening things a lot more than we'd like to. So the data that we used, and our objective was to look at, one was to try to get a better idea of whether a slope is stable or unstable, and also to just get a larger, more diverse data set to try to wash out some of the noise in this data. So first we compiled a data set by having a bunch of avalanche forecasters in the western US dig snow profiles and do stability tests, which lasted for 4 seasons. And Doug set up a field in SnowPilot for anyone who was participating, so that they could, and I'll go into more detail about this, but so they could, before they did any tests, they put a slope stability rating, what they thought the slope was, what the stability of the slope was before they did a test, and then also after. And then we also pulled data from SnowPilot from 2007 to 2020. We pulled out all snow profiles that had at least one of these stability tests and also had either a slope stability rating or a sign of instability noted with that pit. And so that gave us 3,300 pits to work with in that data set. So in each of those data sets, to define what the actual observed stability is, what we thought whether the slope was stable or unstable that the tests were being performed on. As I said, we had the forecasters rate the slope's stability using this scale that's adapted from snow, weather, and avalanche guidelines before they did any tests. And we did that so that the test itself wasn't influencing so we could get an idea of what they thought the stability was before they got that stability test data, to avoid sort of a circular logic. But then they also have the rating after they did the test, and so that's some interesting data there. And this stability scale is typically very good, good, fair, poor, and very poor. But since we didn't want people to just call things fair, as they often do, we forced them to choose either fair stable or fair unstable, so that we could group things binarily as either pits done on stable slopes and pits done on unstable slopes. In the SnowPilot data set, if there was a stability rating on the slope, we use that. On the pit profile, we use that to label a slope as either stable or unstable. And if it wasn't rated, or if it was rated fair, because in this data set they don't have the fair stable, fair unstable, then if there were signs of instability like avalanches or collapsing on similar slopes, we put it in the unstable category. If it was fair without any of those signs, we put it in the stable category. If there was no rating or no signs of instability, it didn't make it into the data set. So our thresholds for each test of whether it was a stable or unstable result, a lot of you probably use these as well. For extended column tests, if it propagated, whether it was PV or P, we called it unstable. If it was a ECTN or ECTX, we called it stable result. For the PST cut lengths that were less than 50% and propagated to the end are unstable. If they're greater than 50% or did not propagate, they were stable results. And then the compression test, we used two different criteria. We had one, we looked at them calling tests unstable if they broke with less than 21 hits. And then we also looked at calling them unstable if it was less than 21 hits or if it had a shear quality of Q1 or a fracture character of sudden collapse or sudden planar. So this one, if it was more than 21 but had a clean shear, we put it in the unstable category. And then to determine false stable and false unstable rates, we put things into a contingency table where for each data set, you count if your test result's unstable and the slope rating was stable, it goes into the false stable box. If your test result's stable and observed stability is unstable, it's in the false unstable, and then these ones that aren't filled in are correctly predicting what we thought or the user thought the stability of the slope was. So then we take the number of false stables and divide it by the total number of stable profiles in that data set to get a false stable rate, and the number of false unstables divided by the total number of false unstable profiles to get that false unstable rate. So for an example, I won't go through this for each one of our data sets, but for the extended column tests that were performed in our professional data set, using the slope stability rating based on their rating before doing tests, we had 30 false unstable results out of 110 profiles that were dug on stable slopes, and a 27% false stable rate. And we had 131 stable test results on slopes that were labeled unstable for a 37% false unstable rate. So we had those two data sets, but we ended up looking at about 4 data sets. So this is what I just showed you the calculations for on the top. When we looked at the professional data set using the slope stability rating after they did tests, those rates dropped quite a bit, about 10%. And then when we looked at the whole SnowPilot data set over that 2007 to 2020 period, we had false stable rates of 23% and false unstable of 41%. And when we removed the 500 and something pits that were in that professional data set were also in this full SnowPilot data set. So I was curious what it would look like if we took those out and just looked at all the other people's pits. Not a huge difference for this ECT test. So our range of false stable rates for the ECT was 16 to 27%, and the false unstable rate of 29 to 44%. For the propagation saw test, those are the results there. So pretty similar false stable and false unstable rates in the pro before and after data sets. And then a little bit higher in these SnowPilot data sets, and especially when we take that chunk of pro pits out. And calling these the professional data sets just kind of for simplicity, I would assume that a lot of pits in SnowPilot in general are done by professionals with varying levels of experience, probably some recreational users, but people who are entering their data regularly typically tend to have some professional involvement. But that's kind of an interesting result that jumps up so much more when we just look at this larger, more diverse data set. And it's kind of an indicator that more experienced users that do the test more are better at selecting when that test is appropriate and actually performing it and keeping the saw on the weak layer and stuff. And whereas the ECT may be a little bit more user-friendly in a wide range of situations. So the range of false stable rates was 19 to 36 for the PST, and for false unstable rates was 34 to 37%. So a fairly similar range. For the compression test, with just the unstable results being less than 21 hits, we were in the 20 to 25% range of false stables, and again, really high false unstable rates up in the 70s. And when we use shear quality, the false stable rate goes down quite a bit to close to 10%, but the false unstable rates then go up. So it's a not really the best trade-off, I guess, in terms of really being accurate and effective. Furthermore, we are interested how often in that professional data set of 562 pits the rating was changed from when the before rating, if it was changed after they did the test. And so we had 437 pits that had a rating of stable before they did a test, and 125 that had a rating of unstable. And 29%, or almost a third of the time, forecasters changed their rating at least one step on that scale of very good to very poor. So not necessarily from stable to unstable, but it did jump, it did move. It might have been from very good to good or good to very good. And 11% of the time, it did change from stable to unstable. So even just this third of a time tells us that these pits are giving us useful information. Even if it's not telling us whether this slope is great to ski right now or not, it's helping us answer a question. We're often going out there looking to see if the snowpack is getting better or if it's getting worse. And this indicates that we are gathering some sort of useful information from these tests. So the general conclusions are that in regards to false stable and false unstable rates, ECTs and PSTs perform similarly when conducted by avalanche professionals. In the more diverse, larger snow pilot data set, the ECTs do have a slightly lower false stable rate and false unstable rate. So as I said, that may indicate that the ECT is a little more user-friendly or applicable in a wide range of situations, and that professionals have a better ability to apply the PST in proper situations and perform that saw cut in the right layer. And then that after performing stability tests, forecasters change the stability rating at least one step, almost a third of the time. So tests are definitely a useful tool for tracking weak layers and assessing slope stability or contributing to slope stability assessments by trained users when they're applied appropriately. And yeah, thanks to all these folks, Eric Knopf, Chris Bilbrey, Alex Dunn, Gabrielle Antonoli, Dave Zinn, Ian Hoyer, Ron Simonhoy, Steve Renard, Andy Anderson, Brendan Schwartz. Those guys are from the Eastern Sierra Avalanche Center. Mark Staples and his crew at Utah, Evelyn Lees, Drew Hardesty, Toby Weed, Eric Trembeth, and Paige Weed, and Brett Kobernick. They all contributed to that professional data set. And Doug and Carl for helping put this research together and get it started and finished up as well. And then Jim Earl for maintaining the SnowPilot database and pulling out whatever data sets we need all the time. Any questions?
It seemed like I remember you guys were asking for some data on wumping in the flats, and I'm wondering if you got much of that. Doing a pit right after you've been out there.
Yeah, I think Doug was working on that with Ron Simonhois and Carl. I think they got a pretty good bit of data. That's not. I don't think any of that's included in here.
It's not included in that, no.
But
So we're still working on that.
Yeah.
I'm not quite sure how to articulate my question, so bear with me. But basically, do the results of this study make it worth revisiting what counts as unstable when it comes to the PST?
That's probably something worth looking at. I don't know exactly, where you draw that line, but there, you could probably.
Like if you were to change the threshold to 70% or 75%, would that make it?
Yeah, or maybe 30% or.
Right.
I think it's something worth looking at. I think that's somewhat, I don't know, Carl, is that kind of is the 50% somewhat arbitrary, or I mean, I
I
know
mean,
there's
it's
kind of a lot
basically
to it.
I mean, the 50% was based on what, Bruce Jameson and Dave Gauthier decided at the time. And it was somewhat arbitrary, somewhat related to some of the data they collected. The problem is you can adjust it any way you want, but if you adjust it and say push it out to 70, you're gonna have a lower false stable rate, but you're gonna have a higher false unstable rate. And then, the same as you adjust it either way. So that's the key. And then the other thing is just that, what everyone has to remember is these tests are they're small. They're really small. And when you do a propagation saw test, like 100 centimeters is probably too short to sort of capture what's going on, because you actually want to sort of form a wave of the bending slab that then propagates, and you get an attraction of the crack from the other side, and that and so you need to form a decent wavelength. You actually, for a 30 centimeter deep slab, you probably need to be at least 120 or 150 centimeters to start forming that wave. But then people have done experiments just using really long ones, and then they found that their false stable rate goes way up. Yeah, because it seems like it should be stable, but it's not. So yeah, so there's just this balance all the time.
Do you think that adding a hard strength score like you do with the compression test into the ECT data would reduce that false stable and false unstable rate? Like
a shear
ECT
quality?
25 stable.
Yeah, and we're kind of looking at that as well, like cutting, saying 23 and below is unstable. If it P23 and below is unstable, and it changes things just a few percentage points from what we've looked at so far, but it does lower it.
So you had the same observer did the forecast before you did the test, and then they made a second assessment, and the only new data that went into it was whatever the test was.
Yeah.
So a lot of that would be how much confidence they have in that particular type of test.
Yeah.
So
Yeah, and they're certainly subject to
doesn't mean
being
much to
wrong
me,
there
say.
too.
But Ed, they were, for a lot of them, we were having them do the rule was you were doing all three tests.
Okay.
So you weren't just going to your go-to, so you had to do all three. So I don't know if that would matter to.
Yeah, no, I just wondering, but that would still be what kind of bias you might have towards these small tests in general.
Yeah.
to maybe
Yeah,
get it
for
right.
sure.
And did you ever do it where you had a group of people who gave their assessment before, and then that same group gave the assessment after the test? Or did they change the same?
No, it was just individuals.
It's always one person.
Yeah, or
one
maybe
test.
it's only individuals submitting it, but sometimes you're there with a partner.
I just wondered if you had 4 people who
Yeah.
gave their assessment without talking, and then you
It'd be
had 4 people
interesting.
after who gave.
But it's certainly a good point that the tests mean something to
What
the
it means
people
to you
who
and what it
are
means to
changing their rating.
It's interesting
The
though.
problem with doing these assessments, of course, is just because of all the variability that exists out there, because you can only test the piece of snow right in front of you once.
Right.
So what happens is, with some of this work is that, you say, okay, this slope is stable and this slope isn't, and that the question is how are you going to define that? And so you say, well, this slope is unstable because there's an avalanche right there. Well, you're testing the snow next to the avalanche that didn't slide. So is it stable snow or is it not stable snow? And then sometimes we look at these different signs of instability, like is there an avalanche, is there cracking, collapsing? But someone sees an avalanche across the way and they're like, hey, there's an avalanche, and then they dig on their particular slope that they're on, and is that really representative of that slope that the avalanche was on or not? And then of course you come back to some of the work that Ian did when he was looking at these extended column tests, where he was looking at the spatial variability across slopes and finding there were slopes that were 50% propagated and 50% didn't propagate. So was that a stable slope or an unstable slope? And no matter which way you cut it, you're gonna have a 50% false unstable and a 50% false, for that particular slope. So I think that, this is just my own personal feeling about it, but, with these stability tests, they're sort of a way for us to think about some of these processes going on in the snowpack at a very small scale. And it just reinforces, because there's so much variability, it reinforces that we never use them to tell us that it's stable. Like, they're just sort of a last check, at least in a recreational setting, they're kind of a last check. In a professional set, you're gonna ski the slope anyway, so you go ahead and do it and see if it gives you some new information. In a professional setting, it's different, because you're going to a lot of different places and you're trying to figure out like what that is, kind of how that's filling out your picture, but there's biases in all these techniques, and there's plenty of biases in what we try to do too, for sure.
But to add to that, Carl, it seems like from a professional standpoint, like these tests actually help us just kind of track what these layers are doing, so we may not be making these decisions whether we're going to ski it or not, but just like, how is this layer evolving? Is it getting stronger? Is it getting weaker, staying the same? And tracking those layers, it seems like as we get in this type of snowpack, but what's kind of interesting is, the false stable of ECT was a lot lower initially than the PST, and then as you kind of distilled everything, they got closer together and not farther apart. But I don't know, I find that if I have any question, I do an ECT and a PST, and I try to make a comprehensive test result and not just put my eggs in one test. So is there a way to, make kind of a more combined test? I know there was a paper on it on a ECT and a Rouge block, combining those two tests to form like a comprehensive stability assessment, basically. But doing that ECT and PST, I think, can sometimes help you put together the initiation and the propagation propensity side of things a little better.
Mm-hmm.
But generally using them to try to determine what those layers are doing.
Yeah, I think I don't think we would stop doing them as forecasters, just because we find where the weak layers are and if they're still propagating or not, even if we think we're on a stable slope and it tells us like maybe with more weight this slope will go, or when we get more snow we need to shoot it, or versus like if you're just going to go to a slope and dig and then open it or ski it, you're kind of rolling the dice.
Kind of rolling the dice, and it's a common message in a lot of the forecast areas across the U.S. is like dig and test, And if you've ever seen just a public rec skier dig and test, sometimes you just kind of want to like hold your head, And so it's like, we give that message to dig and test, but we're relying on these people to do that, to like make some sort of informative decision based on that info. So like, I don't know, like trying to maybe promote like do multiple tests.
Yeah.
And see.
Well, we try to also, like Carl said, like use the try to make it a conservative message of like, if you're going to do it anyway, at least check, and if it propagates, go somewhere else. Or even sometimes we get as conservative as like dig, and if you see the weak layer, go somewhere else.
And a lot of times just by sticking a shovel in the snow, you can learn a lot.
Or like this year, we're like, if it's an ECTN because there's a weak layer there, like you might not want to trust it.
But if I'm doing an ECT and a PST and I get one unstable result on either one of those tests, that's an unstable. Like, that's what I'm thinking on.
Yeah. But and with either one, the user needs some level of training with it, for it to, whether it's digging it in the right spot or being able to cut the weak layer correctly. I
was wondering if there's enough info in the data to stratify the results by problem type or layer depth.
That's a good question. I don't know if our data set's quite big enough. just because the more you like pull out those variables, each group gets smaller and smaller. But I think there's definitely something to be said for one test might be more appropriate in certain situations than the other, and I haven't looked at the data for what that is exactly. Like anecdotally, I have some feelings about it, but but it's probably true to some extent.
I think there's a video by Jameson on that, isn't it? On just which stability test works best
Okay.
with different layers. I believe so. I'm curious about it.
Mm-hmm.
So I had this great idea once, a study I was gonna do. I would isolate a column and do a CT test on it, and I'd do one next to it or something, and I'd artificially weight it with like an inch of water, that much weight on it. And I wanted to do that before that and do it with that weight on there, and then let it sit for a while and see if it stabilized, if the weak layer got accustomed to that new weight, if I would get lower scores after waiting. But so in my pits, what I was doing was isolating columns next to each other, and I'd do a CT test on one, and then I'd put an inch of water weight on the next one and see what scores I'd get. And then I'd maybe do the next one next to it without weight. And my results were varying. I couldn't even get a lower score with the inch of water on there. I was basically getting the same results, same number of taps. And even so within my snow pit, there's enough variability that my results were, I couldn't come to any conclusions. So trying to artificially load a column, multiple ones, and then doing the CT test on them, like 1 hour later, 2 hours later, 5 hours later, 6 hours later, I wasn't getting enough different results to be significant. So I just came away with thinking, well, that study ain't gonna work. I can't even get a different result from one that's loaded artificially and one that isn't. So yeah, I don't put a lot of weight in those tests other than identifying the weak layers and stuff, and it's just, I couldn't correlate anything. You think, well, you put an inch of water on there, I should get a lower score, but basically I couldn't, not reliably.
Yeah. Carl did some stuff similar to that.
You can with a propagation saw test.
Okay.
Like
The
what
cut lengths
happens
are getting
is
shorter.
that the more load you add to the propagation saw test artificially, the shorter your critical cut length. So, and then also if you load it, you'll have a very short critical cut length, and then if you leave it loaded, that critical cut length increases over time. So, basically mimicking what we see in terms of the sensitivity of the snowpack in terms of loading and time.
Can you correlate that to the more weight on it or just a better slab?
You can correlate it just to the load, to the amount of additional load that you added. In large part, that's because you have that being, it's different than a compression test. Like with a compression test, also, if you put a block of snow on top, you're also going to introduce some differences there in terms of how your tapping force is going to go down. But with the propagation saw test, by adding, by adding additional load, then as you cut the weak layer, you get more bending moment in your slab. That bends more, and that helps get that fracture started and driving more quickly than if you don't have that additional load. And then ultimately, the fact that your crack length gets longer over time is due to two factors. Your slab is getting stiffer and your weak layer is getting stronger. So, and we're able to quantify both of those.
So when you add just the weight, one's a static load, and the other one you're thumping. The propagation saw test, you're putting a crack in there, but it's still a static load.
Yep.
The other, and I'm not sure what it means, but the other one is a static type of load. So that pressure bulb that we talked about earlier that's what you only see is a static load. And if you put an impact load on it, we all know it's a different way of loading it. I'm not about to take away from that, but I'm just saying that putting a little more weight on it is not the same as hitting it with a similar type of force. It's transmitted differently.
I'm curious why, when you're using the fracture character to try to differentiate a little bit in the CT, why did you only do it for the hard loading steps?
I think because previous research had used that. But yeah, you
I
could.
feel like a lot of that false unstable is probably resistant fracture characters.
Yeah, you could just take out the loading steps and just look at tests that had Q1 or sudden collapse. Yeah, I haven't, but it would be worth taking a look at. I don't think I did.
85% false unstables.
Yeah, that might help. Right. Can save your questions for Carl later.
I'll answer all questions. All right, thanks a lot, Alex.